Hi, everyone. I'm going to start off by kind of introducing the quadratics unit to you. Today, we're going to talk about what the parent function looks like, and we'll kind of talk about a couple of properties of the graph, and then we'll go back and talk about some AH and K things. So we're going to talk about quadratic functions in this unit. Quadratic functions are degree 2 functions, meaning that we're going to have an x to the power of 2 somewhere in our function. This is the most simple quadratic function that you could graph. That's just f of x equals x squared or y equals x squared. And what we want to do with this simple function is we want to create a parent table of values for our quadratic function. We had one for the absolute value function. And we're still going to use the same x value. So we're still going to want to use -2, -1, 0, 1, and 2, because those are really easy values. But to get the y values of the parent table of quadratic functions, we're going to use this y equals x squared. So if I know y is equal to x squared and my x value is -2, well, -2 squared is really telling us to do -2 times -2, which will give us a y value of 4. If my x value is -1, y is going to be -1 squared, or -1 times -1, which is +1. If my x value is 0, y is going to be equal to 0 squared. 0 squared is just 0. If my x value is 1, y is going to be 1 squared, which is just going to be 1. And if my x value is 2, my y value is going to be 2 squared, which is going to be 4. So this is going to be the parent table of values that we're going to want to use when we are graphing our quadratic functions, in vertex form anyway. And this table of values, if we were to graph it on a coordinate plane, gives us something called a U-shaped graph, and it's specifically named a parabola. So if I were to graph this, if I were to kind of pretend like this is my coordinate plane, we'll look at an example of kind of what this looks like a little bit neater later on. If I plot these points, -2, 4, oops, that should be up there, -1, 1, 0, 0, 1, 1, and 2, 4, my graph is going to look something like a U-shape curve, something like this. So that's what a general shape of a parabola looks like. That's kind of what the parent function looks like. There's some special things that we want to talk about when we talk about quadratic functions. One of them is either the lowest or the highest point on the graph, and that is something called the vertex. We knew that the absolute value function had a vertex, and the parabola also has a vertex. So the vertex of this parent function is the lowest point on the graph, which would be right here at the point 0, 0. So that's our vertex. And then there is also this thing called an axis of symmetry. And sometimes you'll see that abbreviated as AOS. And this is kind of an imaginary line that literally cuts the parabola in half. And we're going to graph this axis of symmetry onto all of the parabolas that we are going to graph today. And what that would look like, if we kind of imagine the line that would cut this parabola in half, that would kind of be going down this kind of y-axis here. That's what our axis of symmetry would do. It would literally split this graph in half. I know my graph isn't perfect there, but that's what the axis of symmetry looks like. So throughout this unit, we're going to be graphing quadratics in 3 different forms. Today, the form that we're going to be looking at is called vertex form. And this is the vertex form that we're going to use. It is f of x equals a times the quantity, and here I'm going to open up a set of parentheses, x minus h. But since we're talking about a quadratic function, I'm going to put a power of 2 up on the outside of the set of parentheses, and then I'm going to put a plus k on the outside. And here's where the A, H, and K are going to come back from when we talked about the absolute value functions in our first unit. So the A value is still having to do with the stretch or the shrink. The A value also has to do with the reflection. The H value moves our function left and right. The K value moves our function up and down. So if we look at this example of our function, just to kind of go back and review our H and K here, our A value of this function is going to be that number out in front of the parentheses, so -1/2. Remember that H is inside, in this case, the parentheses, but remember that H always gets the opposite sign. So since it's plus in here, our H value is actually going to be a -2. And then this K value is going to be kind of this value that's kind of trailing along on the outside. K value keeps its same sign, so K is going to be 5. So this is telling us that since A is negative, that means that there's going to be a reflection. Because remember that whenever A is negative, there's going to be a reflection, which means that if there's a reflection, our graph is going to be opening downwards. So I'm going to write here, since A is negative, the graph is reflected. And opens downwards. So since A is negative, the graph is reflected, and therefore it opens downward. And then to determine if we have a vertical stretch or vertical shrink, that also has to do with our A value, and we want to compare our number here to 1. So we're really looking for the absolute value here, because remember that the negative only has to do with reflection. So if we're saying that we want to look at the absolute value of -1/2, that's going to give us a +1/2, and then we need to compare that number to 1. Well, since the 1/2 is less than 1, that means that we're going to have a shrink. So here we have a vertical shrink. And that is because 1/2 is less than 1. Or in between 0 and 1. And then here's where the H value comes in. And that's going to have something to do with our axis of symmetry, which we'll see in the example. But our axis of symmetry is always an equation of a line. It's always going to be a vertical line. So vertical lines always have an x equals equation. And our x equals is going to be whatever our H value is. So since our H is -2, our axis of symmetry is going to have the equation x is equal to -2. And it's going to be a vertical line at the x value of -2. And then similar to the absolute value function, the vertex of this function is going to be whatever our H value is, comma, our K value. And in this case, our H is -2. Our K is +5. So our vertex is at the point -2, 5. So we're going to talk about how to use all of this information to graph the function. So we're using the same equation that we just kind of talked about, all these pieces up here. The first thing that I always do is I plot the vertex. So I know what my H and my K are. So I'm going to go ahead. I'm going to say I'm going to put the vertex at the point -2, 5. And there's my vertex. And the nice thing about plotting the vertex is you can always use your table of values to check to see if your vertex is correct. And actually, I'm going to go ahead and label that too. It's my vertex. And I'm going to set up the parent table of values that we set up from kind of that first thing that I started talking about in these notes. So -2, -1, 0, 1, and 2 are still our x values. Our y values are now 4, 1, 0, 1, and 4. And then the x values are going to be moved by whatever the h value is. So since h is negative, we're going to take all of our x values and we're going to subtract 2 from them. So -2 minus 2 is -4. -1 minus 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. 2 minus 2 is 0. So these are going to be the x values that we're going to end up graphing on our coordinate plane. But then we need to transform the y value. So the first thing I need to do is multiply by my a value, which is going to be -1/2. I want to multiply all of my y values by -1/2. So 4 times -1/2 is -2. 1 times -1/2 is -1/2. 0 times negative 1/2 is 0. And then I end up getting negative 1/2 and negative 2. And then I want to take the values that I just got and I want to add or subtract on the k. In this case, I want to add the k value since the 5 is positive. So I'm going to take all of these values that I just got and add 5 to them. So that's going to give me a positive 3, positive 4.5, positive 5, another 4.5, and another 3. So here's the x or the y values that I want to graph. So the x values here, negative 4, negative 3, negative 2, negative 1, and 0, and then these y values. One, 2, 3, 4, 4.5. Here's the vertex, negative 2, 5. I've already plotted that point in. And that's kind of a good way to check your work. Your vertex should always be found in the middle of your table of values. And then I'll plot my other 2 points here. And I should have kind of the beginnings of kind of a U-shaped graph here once I plot those points. So then I'm going to go ahead and make my actual graph here. And similar to the absolute value function, you always want to make sure that you're putting arrows at the ends of your branches because they're going to continue. And make sure that it is U-shaped. This is not an absolute value function, so we don't want to look like a U or a V. We want it to look like a U. And then the last thing I want to do is I want to sketch the actual axis of symmetry. So we said that that was at the line x is equal to negative 2. So here's my x value of negative 2. And I'm going to make myself a vertical line, but I'm going to dot it in. And I'm going to label it my axis of symmetry. And that's a good way to determine if you've graphed your points correctly too, because at the x value of negative 2, that should be that line that's cutting your graph exactly in 2 halves. So we'll do one more example together, and then we'll talk a little bit about some applications. Okay, so now we're looking at the graph of f of x equal to 2 times x minus 5 squared plus 1. So I'm going to pick out my a, which is going to be 2. Be careful, h here, since it's negative in here, it's going to be positive here. So positive 5. K would be negative 1. And now I want to determine if the graph is going to be opening upwards or downwards. Well, that has to do with our reflection. So is A positive? Yep, A is positive. So that means that there's no reflection. So that means that we have to be opening upwards. So I know there's no reflection. That's because A is positive. So there's got to be opening upwards. And then my axis of symmetry is at the x is equal to h line. So that's going to be at x is equal to 5 because that's what my h value is here. My vertex is going to be h comma k. So my vertex is 5 comma negative 1. And then we'll talk about the domain and the range after we graph the function. It's easier to look at a graph than try to determine the domain from not looking at anything. So I'm going to go ahead and set up my parent table of values again, just from what we kind of talked about again in that first example. So negative 2, negative 1, 0, 1, and 2 for the x values. Y values are now 4, 1, 0, 1, and 4. So then since my h value is positive 5, I'm going to add 5 to all my x values. So 3, 4, 5, 6, and 7. Multiply my a times my y. So a is 2. So 2 times y is going to give me 8, 2, 0, 2, and 8. And then k value is negative 1 here. So my last column, I want to take those values and subtract 1 from them. So 7, 1, negative 1, 1, and 7. So here's the x values I want to graph. So 3, 4, 5, 6, 7. Here's the y values that I want to graph. 7, 1, negative 1, 1, and 7. So I'll go ahead and plot those. 4, 1, 5, negative 1, 6, 1, and 7, 7. And again, remember that your vertex should be this middle point here. So we said vertex was 5, negative 1. There it is, 5, negative 1. So once I'm done plotting those points, go ahead and connect with a U-shaped graph again. We don't want a V here. And then I want to draw in my axis of symmetry. My axis of symmetry should be at x equal to 5. So 1, 2, 3, 4, 5. Yep, there it is right in the middle of my graph. And I'll just make myself a dotted line here. And label that my axis of symmetry. So similar to the absolute value function, if we're talking about the domain, remember that the domain is our x values, or we read that left to right. Since we have arrows here, that's actually indicating that our graph would be kind of opening wider and wider and wider as the x values go on. So our domain is actually going to be all real numbers, or negative infinity to positive infinity. And then remember that the range is read from the bottom of the graph to the top. So the bottom y value here is -1. We're extending up to positive infinity. So the range is going to be from -1 to infinity. Infinity is going to get the parenthesis. Since this dot is closed, the -1 is going to get the bracket. And so we know that our graph opened upwards. We knew that our vertex was at 5, -1, and our axis of symmetry was at x equal to 5. And our table helped us to determine that as well. Okay, so now we want to talk a little bit about some applications. Applications can be a little bit tricky, but I'm going to show you guys kind of an easy way to determine what the variables are that you're dealing with, which I think is a lot of time kind of the problem or the trouble part of these types of problems. So I'm going to write my standard form for my quadratic function again. So we said that that was f of x, or remember, f of x is just a fancy way of saying y is equal to a times x minus h squared plus k. And what I'm going to do is I'm going to match up here the variables that I have. So in the y, where the y would be in this example, that's where the h of x is. And then I have negative 0.025 times x minus 20 squared plus 10. And what I'm going to do is I'm going to take these values and I'm going to pick out what I know. So I know that a is negative 0.025. I know that h is going to be positive 20. Again, because it's negative here, it's got to be positive here. And I know that k is going to be 10. And this gives me a lot of information about what this graph is going to look like, even without knowing what it looks like. So I know that the graph is going to be reflected, or it's going to be opening downwards because the a value is negative. And I also know that because my h value is 20 and my k value is 10, my vertex is going to be at the point 20, 10. So if I were to just kind of sketch a graph of the soccer ball's path, now I know that my graph is going to be opening down, and I know my vertex is going to be at the point 20, 10. Okay, so let's make this, let's count by 5. So 5, 10, 15, 20, 25, 30, 35, 40. So I know my graph is going to be opening down, so that means it's going to be kind of an upside down parabola, and I know my vertex is at 2010, so I'm going to go ahead and graph that in. So my graph is going to probably look something like this. And since I know that through the vertex is where the axis of symmetry is, I want to make sure that the other side of my graph looks pretty symmetrical to this part of the graph. So since my halfway point is at 20, that would mean that I would want to end my graph over here at 40, which I didn't do a very good job of like scaling this, so it's going to look a little uneven, but that's what the graph of my soccer ball would look like. So now that I know what this graph looks like, now I need to determine what the variables are. So it's telling me x is the horizontal distance that the ball travels. So this means that my x-axis is my horizontal distance. And h is the height. And if we look at where h is, the h values are actually standing for where our y values are. So that means that our y-axis over here is actually going to be the height of our ball. So x is our horizontal distance and the y's are representing the height. And this is going to help us to determine what the answers to these questions are going to be. So in part B, it's asking you, what is the maximum height of the soccer ball? Well, maximum just means what is the tallest height or tallest point. Well, if we look to see where the graph is the tallest, well, that's going to be at that value of 10. So that means that the tallest point here is at the y value of 10. So that's telling me the maximum height is 10. I think my units here are meters. So the maximum height of the ball is 10 meters. And then it's telling me to estimate the horizontal distance. So horizontal distance is our x-axis here. So I'm looking for a distance along the x-axis that the ball travels before it reaches its maximum height. Well, we know that it's reaching its maximum height up here. So that means that the horizontal distance that we're traveling before it reaches its maximum height is actually 5, 10, 15, 20 meters. So I'm going to say the ball travels a horizontal distance of 20 meters. And then part D is asking us to estimate, again, the horizontal distance. So again, we're looking for something along the x-axis here because that's where our horizontal distance is. The ball travels from the time it is kicked to the time that it hits the ground again. So if we're kicking it where the ball is starting and the ball is going up here, we know that that's a horizontal distance of 20 meters that's been traveled. Well, when it hits the ball again, or when it hits the ground again, it's going an additional 20 meters. So the whole horizontal distance that we're traveling across when the ball is kicked to where the ball lands is actually going to be this entire distance across. So that's going to be a total distance of 40 meters. So the ball travels a total horizontal distance of 40 meters. And for these questions, it's a lot easier to start off with a graph or what the kind of balls travels looks like, because it's a lot easier to go and look at what the graph looks like to help you to answer these questions. So we'll look at one more similar type question. So now we're talking about fireworks. So the path of a firework is described by this function. H of t is equal to negative 4.9 times t minus 5 squared plus 124, where h is the height of the firework in meters and t is the time in seconds after the launch. So again, similar to what I did in the last problem, now I actually have some room to write it above. I'm going to write this as y is equal to a times x minus h squared plus k. And I'm going to go ahead and label my a, my h, and my k. So a is negative 4.9. H again, careful of your sign here. Since it's negative here, it's going to be positive here. So positive 5. K is positive 124. And again, this is telling me a couple things. A is negative, so the graph is opening down. And then the H is 5 and the K is 124. So our vertex is at the point 5, 124. So again, I'm going to just do a kind of a quick sketch of what this looks like. And actually, that's actually asking us to do that in part B. So I'll count by ones here. So 5, 6, 7, 8, 9, 10. Let's see, I'll count by maybe 20s here. So 20, 40, 60, 80, 100, 120, 140, 160. So my vertex is going to be at 5, 124. So maybe somewhere around here. And I know that that's, again, going to be kind of like my halfway point. But before I sketch in the path, this one's a little bit different from the last question. And I want to know how high off the ground is the firework being launched from. So what I would need to do here is I would need to figure out what my initial value is going to be, or where I'm starting my firework launched from. So what I need to figure out is when my time, because T is time in seconds after launch, I need to figure out what time I'm starting at, which is going to be 0, and I need to plug that in here. So I'm going to write here the firework is launched at a time of 0. So what I'm going to do here is I'm going to do a little bit of algebra, and I'm going to plug in 0 anywhere in my equation I have a t. So I'm going to plug in 0 for here. I'm going to do a little calculation. So that's going to be negative 4.9 times 0 minus 5 squared plus 124. Simplify in the parentheses first here. So that's going to be negative 4.9 times negative 5 squared plus 124. And that's going to be negative 4.9 times negative 5 squared is 25. And then I'll just use my calculator here to do that. Negative 4.9 times 25 plus 124. And when I do that, that's telling me that I'm actually launching 1.5 meters off the ground. So that means that our firework actually isn't being launched directly from the ground. My firework is actually being launched a little bit off the ground. So maybe there's like a platform or something that our fireworks are being launched from. And here is where we want to determine, okay, well, we know that our vertex is at that point 5, 124, but what do these values mean? What does this mean on the x-axis? What does this mean on the y-axis? So if we look back up to where our equation was here, this is telling us that our x and our t are in the same place. So that means that our x-axis in this graph is actually representing time. So this stuff that I've labeled kind of down here on the bottom of my graph is actually being represented as time. So the x-axis here is time. And again, our y is where our h is. So that means that our y-axis is going to be our height again. So that means that our height isn't going to start right here at our vertex. Our height is going to start a little bit above, kind of taking into consideration that we're launching 1.5 meters off the ground. So I'm actually starting a little bit above the vertex. And then I can go ahead and sketch in my graph of my firework. And it probably looks something like this. So then it's asking me, once I kind of know that that's what the path of the firework is looking like, what is the maximum height? Well, its highest point here, I know it doesn't kind of look like that on my graph, but my highest point should be my vertex point. And we know that that's going to be at a height of about 124 meters. So I'm going to say the maximum height is 124 meters. And it's asking me after how many seconds does the firework reach its maximum height? Well, it's reaching its maximum height. If we look along this axis again, the axis is representing time, and we're looking for how many seconds. So that means that we're looking along the x-axis. So it looks like we're about 5 seconds from the time that we're launching to the time that we're reaching our maximum height. So after 5 seconds, the firework reaches its maximum height. And then our last question is to determine the height of the firework 3.5 seconds after it is launched. So if we're looking for the height, we're looking for what h is equal to. And it's telling us that we want to know 3.5 seconds after it's launched. So this is actually telling us that our t is 3.5. So we're going to do something pretty similar to what we did in example A. And we're going to say, okay, well, h is going to be equal to this negative 4.9 times t minus 5 squared plus 124. That's the equation that we were given. And it's asking us to plug in 3.5 for our t. So that's going to give us negative 4.9 times 3.5 minus 5 squared plus 124. That's negative 4.9 times negative 1.5 squared plus 124. And I'll just use my calculator here to do the negative 1.5 squared. That's really asking us to do negative 1.5 times negative 1.5. So that's positive 2.25. And then I'll have my calculator just do this out. So negative 4.9 times 2.25 plus 124. And that gives us 112.975. So the height of the firework after 3.5 seconds is 112.975 meters. And that kind of makes sense if you think about the reasonableness of what the answer is giving us here. We know that our maximum height is 5 seconds after it launches, and we know that our maximum height is 124. So if we're not quite at 5 seconds yet, then we're not going to be quite at 124 meters yet. So that makes sense in the context of the problem. Okay, so what I'm going to have you guys do is do some practice on the homework and let me know if you have any questions.